Yes, we continue with polynomial equations, and then we look in this case to polynomials in several variables. Okay, so up to now we considered polynomials in one variable, like maybe just x or y or z, just one. But in many applications, we encounter functions of several variables. For example, we can have x and y, we can have x, y, and z. So you have them together in one polynomial. So a polynomial in several variables is built from variables like x, y, z, real or in this case complex even coefficients, and the operations of addition, subtraction, and multiplication with non-negative integer components on each variable. So when we're looking at just a single variable, I think there was an insistence on the fact that the coefficient had to be real. But when we talk about several variables, it looks like complex variables, complex coefficients are also allowed. Okay, although for the most part we stick to real coefficients. Okay, but of course, when it comes to the exponent, nothing changes. It has to be an integer and it has to be positive. So it is non-negative integer exponent all the way. So let's talk about polynomials in two variables, and we have the general form. So a polynomial in x and y, for instance, can be written as a finite sum of terms of the form. So take note, finite sum. So it means it's not like when we were working with series where you have infinite series and all that. So you can have a polynomial of this type as a finite uh, sum of the form aij, xi, yj. For instance, maybe you can have A it can take any shape. It can be anything at all. And then you have X, I, J like that. So maybe you can have A00, X0, Y0. In that case, I mean, everything is A0, everything is constant in that case. That's a constant term. And then you can have, say, A01, X0, Y1, meaning that you have just A01 with only Y because X raised by 0 is 1, and so on and so forth. So here, the AIJs are real or complex numbers called coefficients. Those are the AIJs. They are the coefficients. Then I and J are non-negative integers, like we know already. So I and J belong to the set of integers that are always greater than or equal to 0. Then only finitely many AIJ are non-zero. Okay, so you hardly have, I mean, you can only have few coefficients that are non-zero, right? Maybe you shouldn't have more than one, that one AIJ that is, yeah. I mean, if the constant, if the coefficient is, if AIJ is 0, then of course it means that term breaks down. Or if all the coefficients are 0, then the polynomial does not exist. That's simply just 0, right? So a general polynomial in x and y looks like p of x comma y equals summation over ij of aij xi yj. So it doesn't have to be only x and y. It can be x, y, z. It can be w, x, y, z, and things like that. So with aij equals 0 for all, but finitely many pairs ij. So aij is only 0 for uh for all but finitely many pairs. So in essence, what we're saying is that aij should not be 0 for the coefficient and for the polynomial to exist. So each term aij, xi, yj is called a monomial in x and y. So each term is called a monomial in x and y. So let's see example 1, for instance. So we have this. We have to consider p of x comma y, which is 3x squared y minus 2xy plus y cubed. So the monomials and their coefficients are as follows. So 3x squared y is a monomial. The coefficient is 3, and the exponents are x2, y1. So the exponents are 2 and 1 in short. Then the second monomial is minus 2xy. So you take it with the sign, don't forget. So minus 2xy. So the coefficient is minus 2, and the exponents are 1 and 1, x raised by 1, y raised by 1. And then y3 is the third monomial. So the coefficient is 1. So if you don't see the coefficient, then that is 1, right? And the exponents are 0, 3, because since zero is, I mean, since x is not there, so that means you can associate it x raised power 0 and y raised power 3. So the coefficient of x there is 0 and the coefficient of y is 3. So we can just simply write it as p of xy equals 3 multiplied by x squared y plus minus 2 multiplied by xy plus 1 multiplied by y cubed. That's an example right there. I mean, that's pretty simple because you're already used to it, but I think it's important to understand this concept clearly. So how about evaluating P of xy at points? At points, right? So to evaluate P of xy, we substitute values for x and y, basically. So at xy equals 1 and 2. So when x is 1 and y is 2, then you can substitute into this expression. So you have 3 into 1 squared into 2, which is y, minus 2 into x is 1, y is 2, plus y, which is 3, you have 2 raised power 3. So you can then have 2, 1 squared is 1, then you have 3 here. 2 times 2 times 1 is 4. 2 raised power 3 is 8. So you can then have 3 times 2, 6, minus 4 plus 8. So 6 minus 4 is 2. 2 plus 8 is 10. So you can evaluate an expression at any given point like that. Then at xy equals 0, 1, okay? X is 0 here. So in short, you can even take it for granted that anywhere x appears in each monomial, it goes to 0. So x is here, it goes to 0. X is here, it goes to 0 because 0 multiplied by whatever is going to be 0. And then all you have left is y. And since y is 1, so y raised by 3 is simply 1. So you have 3 into 0 squared times 1 minus 2 into 0 times 1, that's 2xy, plus y cubed, that's 1 raised by 3. So 0 squared is 0 times 3 times 1, that's 0. 0 times 2 times 1 is also 0. Then 1 raised by 3 is 1. So everything is 1. So if you evaluate this expression at 0, 1, you get 1. Okay? So we can take example 2 in that case. Let q of x, y be 4x cubed minus x squared y plus 5y squared minus z. So 4x cubed is the first monomial with coefficient 4 and exponents 3 and 0 because the exponent of x is 3, the exponent of y is 0 because y is not available there. The second monomial is minus x squared y, so the coefficient is minus 1, and the exponents are 2 and 1 for 2 for x and y for 1. And then the third monomial is 5y squared with coefficient 5, exponent 0, 2. I mean 0 and 2. 0 for x and y for 2. I mean 2 for y. Then the last monomial is constant. That's minus 7. So that's constant term minus 7. And the coefficients, the exponents are 0, 0 because, x and y simply do not exist there. So that means the power of x is 0 and the power of y is 0. This is a polynomial in two variables with 4 terms. So this polynomial k of x, y is actually a polynomial in two variables x, y with 4 terms, 4x cubed minus x squared y plus 5y squared minus 7. Okay? We have that. Then we have example 3, where we have r of x, y to be 2x raised power 4. I mean 2x raised power 4y plus 3x squared y cubed minus 5x y squared plus 9. Okay, the three this is a two variable polynomial with four with 5 monomials, right? So what do we have? We have 2x raised power 4y is a monomial with exponents 4, 1. 3x squared y cubed is a monomial with exponents x to y 3 minus 5x y squared because the coefficient is minus 5 and the exponents are 1 and 1, 2. Then 9 is a constant term which can be written as 9x raised power 0, y raised power 0. All these are monomials in x and y, even the constant, because we can write it as n x raised power 0, y raised power 0. And then we go to example 4, where we have this in factored form. Polynomials in two variables often appear in factored form. For example, s of x, y equals x plus y into x squared minus y. So you can have it in factored form this way. This is still a polynomial in x and y for sure, written as a product. So you can then expand it. So if you expand, yes, in one of the previous videos, we did multiplication, of polynomial. So that's simply what to just do here. So you can do the FOIL form. So first, outer, inner, and last, right? So x times x squared, x cubed, x times minus y minus xy, y times x squared, that's plus x squared y times minus y, that's minus y squared. And that's just what we have. So in expanded form now, this same polynomial with two variables is the same as x cubed plus x squared y minus xy minus y squared. Of course, the other method you can use is to have the box method where you have xy on the rows, and then you have x squared minus y on the columns, and then you multiply and you get the same results. Okay, for 4.2 now, okay, we have this that we want to talk about degree in each variable versus total degree. So for polynomials in several variables, now you have each variable has a degree, and we have a total degree. Okay. So, and these are of essence, seriously. So for polynomials in several variables, we distinguish between degree in each variable, for example, degree in x and degree in y. And then we also have the total degree of a monomial or of the whole polynomial. So the total degree is the degree of the whole polynomial. All right. So degree of a monomial in two variables, for instance. So a general monomial in two variables has the form, like we said, x raised to power I, y raised to power j. So I and j are the powers. So, or if you can have a coefficient a multiplied by x raised to power I, y raised to power j, where a must not be zero, like we've always been saying, with I and j being non-zero, non-positive, non-positive integers, right? So because I and j can be greater than or equal to 0. So here, the degree in x is I, because you have x raised to power I, y raised to power j. So the degree in x is I, the degree in y is j, right? And then the total degree is the sum of these two degrees. So degree of x raised to power I, y raised to power j is I plus j. So the total degree will be the sum of the degrees of each variable. So if you include a non-zero coefficient, writing a x raised to power I, y raised to power j, the degrees do not still change. So a does not, the coefficient does not affect the degree. That's what that is telling us. So you have each variable has its own degree, and the whole polynomial has a total degree, which we can, which is the sum of the degrees of each variable, and that gives the degree of the total polynomial, of the whole overall polynomial. So degree of a polynomial in each variable. So let p of x comma y be equal to summation I comma j, aij, xi, yj. So like you have several expressions, maybe 3xy, 3x squared y plus 3xy squared plus 3x, just to keep having all of that. So with not all aij equal to 0, we've said that already. So the degree of the polynomial in x is simply the degree of the polynomial in x is equal to the maximum for the maximum value of I, such that j with aij is not 0. So if aij is 0, of course, that breaks down. Then the degree of the polynomial p in y is degree p sub y, which is the maximum j for every x, such that I, rather, with aij is not equal to 0. So let's talk about total degree of a polynomial now. Based on that, so with this example, you get the gist right there. Okay, first of all, we've talked about the degree of a polynomial in each variable. So a polynomial has a degree in each variable, and then it has a total degree. All right, that's the next thing you're looking at. So total degree of a polynomial, the total degree of P is the largest total degree among its non-zero monomials, right? So degree P is simply the maximum value of I plus j, such that aij is not 0. So as far as we have the term, so if you add all the exponents of x and y, if you add all together, like imagine you have like 5 monomials making up the polynomial, right? So if you add up the value on top of x and y for each one, so the biggest of these sums is what will be the total degree of a polynomial. Here, I plus j is the total degree of the monomial, where x is x for x raised power and monomial x I raised by I, y raised by j. So that takes us to example 5. Okay, so we have example 5 now. So P of x comma y is 3x squared y minus 2xy plus y cubed. So you have the following monomials. 3x squared y has exponent ij, which is 2, 1, 2 for x and 1 for y. So the degree in x is 2, degree in y is 1. Total degree is 2 plus 1, that's 3, easy, okay? So, and then the second monomial is minus 2xy, which has exponents 1, 1, because the power of x is 1 and the power of y is 1. Then that means the degree in x is 1, the degree in y is 1. Total degree for that monomial is 1 plus 1, which is 2. So the sum of the degrees of these 2 degrees for each variable. And then for y cubed, it has exponent 0, 3 because that's x raised power 0, y raised power 3. So you have 0, 3. So degree in x is 0, degree in y is 3. Total degree is 0 plus 3 equals 3. Okay? So that takes us to the idea of the degree of the polynomial itself. So how do we talk about the degree of a polynomial in terms of the degree of the individual monomials? So the degree of the polynomial p of x comma y. From the previous cell, you remember that the degree of the polynomial x, so for all the x's, right, we have 2, 1, and 0 for all the x. So the degree of the polynomial in terms of the overall polynomial in terms of x will be the maximum of 2, 1, and 0. That is simply 2. And then for the degree of the polynomial in terms of y, so you go for all the y's. So for y, you have 1 here, you have 1 here, and for the last one, you have 3. So that means the degree of the polynomial in terms of y is 1, 1, 3. So at the end of the day, the overall degree of the polynomial is simply the biggest of the total degrees. So these 3, these 2, and these 3. So automatically, that the degree of the overall polynomial is the maximum of the total degrees. That's 3, 2, 3, which is simply 3. So it means that in terms of x, the degree of the polynomial is 2. In terms of y, the degree of the polynomial is 3. But total degree of the polynomial is the maximum of the total degrees for each monomial, which is 3. Okay? So we can say that p of x comma y has degree 2 in x, degree 3 in y, and total degree is 3. That's basically what that tells us. So we can have example 6, where we now have this. So for example 6 now, let q of x comma y be 4x cubed minus x squared y plus 5y squared minus z minus 7 rather. So we have 4 monomials, 4x cubed minus x squared y plus 5y squared minus 7. So we have all of them here. So the degrees in terms of x and y respectively are 3, 0 because there's no y here. Then 2, 1 because power of x is 2, power of y is 1. Then 0, 2 because there's no x here, but there's y. The power is 2. And then here it's constant, so that's 0, 0. So the total degree here is 3, 3 plus 0 is 3. The total degree here is 2 plus 1, that's 3. Total degree here is 2, total degree here is 0. Okay? So those are monomials and total degree. So it means that the overall degree of this polynomial is simply 3 because that will be the biggest of all the total degrees. So that will be 3. So this is a polynomial of degree 3, although in terms of x, so in terms of x, it's a polynomial of degree 3 in terms of x, and it's a polynomial of degree 2 in terms of y. But in terms of total degree, it's a polynomial of degree 3. Okay? So we'll talk about degrees of the polynomial k of xy now. Oh, that's the same thing we are saying. So from the previous cell now, from here, right? We say degree of polynomial q, okay, in terms of the degree of polynomial q in terms of x will be the maximum of 3, 2, 0, 0. So that's 3. The degree of polynomial q in terms of y will be the biggest of 0, 1, 2, 0, which is 2. And the degree of the overall polynomial q will be the biggest of 3, 3, 2, 0, which is 3. So q of x comma y is degree 3 in x, degree 2 in y, and total degree is 3. That takes us to example 7, where we consider r of x comma y, which is x raised to power 4 and y raised to power 5. So in this case, in terms of x, the degree is 4. Okay. In terms of y, the degree is 5. And the total degree is 4 plus 5, that's 9. So this is a polynomial of degree 9. So the total degree can be larger than the degree in each individual variable. Of course, that's what we have seen all along. Okay. So this is a 2-variable polynomial with degree with 4 with degree 4 in x, degree 5 in y, and total degree 9. So example 8 now. Let x of x comma y be x raised to power 4 plus x raised to power 2 y raised to power 3 plus y plus x y raised to power 5 plus y raised to power 7. So x raised to power for the first monomial now. So the power of x is 4, the power of y is 0 because y is not there. So that's total degree of 4, x2, y3. So that's 2 for x or 3 for y. Total degree is 5. X power is 1, y is 5. Total degree is 6. Y, x is 0, y is 7. Total degree is 7. So now we can say that the degrees of the polynomial will now be this. So that's degree of polynomial s in terms of x is the biggest of 4210, which is 4. And the degree of the polynomial s in terms of y, that's the biggest of 0357, and that is 7. And the degree of the overall polynomial is the biggest of 4567, and which is 7. So the total degree of s of x comma y is 7, right? So let's talk about simple classification for multivariable polynomials. So polynomials in several variables can be classified in several ways, right? So we can classify by number of variables, okay? We can classify by number of variables. We can classify by total degree. I mean, now we've seen degree. So linear, that's when the degree is 1. Quadratic, when the total degree is 2. Cubic, when the total degree is 3, and so on. Now we have quartic, when the total degree is 4. You have quintic, when the total degree is 5. So we can also classify by number of terms. Like you can have a monomial polynomial, meaning that the polynomial only has one term, like the last one we considered. This is, oh, is it the last one? I think second to the last. So this r of x comma y is a monomial. That's only one term, okay? We can classify, if it has two terms, we say it's a binomial. We can just simply say it's a binomial. If it has three terms, we say it is trinomial, and so on and so forth. So we can also classify by whether they're homogeneous or non-homogeneous. Now, the concept of homogeneous and non-homogeneous is just coming up, so we'll see what that means as we proceed. Okay, so classification by number of variables. So you can have univariate. You can have a univariate polynomial which involves only one variable. That's what we've mostly considered from in the first 3 videos. So example is f of x equals 3x squared minus 2x plus 5. So just variable x. Then we can have a bivariate polynomial which involves 2 variables like the ones we've been considering here too. So p of x comma y. So you see this is f of x. This is p of x comma y, which is x squared plus xy plus y squared. So you have x and y in the as variables. Then you can have trivariate polynomial which involves 3 variables. So example is g of x comma y comma z, which is x squared plus 2y squared plus 3z squared minus xyz. Or you can have it. You can have any term, any of the terms as far as the 3 variables appear. Then you can also have a multivariate polynomial which involves more than one variable. That's the general term, right? So multivariate starts from 2 upwards. So like that, except that the earliest ones bivariate, trivariate, and multivariate. So in this section, our examples are mostly bivariate polynomials. I mean, what we've been doing under these polynomials in several variables, we've been focusing more on bivariate polynomials from everything we've been doing so far. So we can also classify by total degree. Classification by total degree. Okay, so we use the total degree, the p of the polynomial. So we can have a linear polynomial where the total degree 1 in 2 variables. So you have ax plus by plus c. So the degree in each case, the highest degree, if you put them together, is 1. So x, you have x1, y0, and you have x0, y1. So if you add the two, 0 plus 1, 1 plus 0, I mean 0 plus, I mean 1 plus 0, 0 plus 1, it's 1. So with at least one of a and b is being non-zero. Then you have quadratic polynomial, that's total degree 2 in 2 variables. So you have ax squared plus bxy plus cy squared plus dx plus ey. So of course here you have for x is 2, y is 0. That's 2 plus 0. The degree of this monomial is 2. Here x is 1, y is 1. The degree is 2. The total degree is 2. Then here cy squared, x is 0, y is 2. The degree is 2. Here you have x0, x1, y0. The degree is 1. Here you have here you have x1, y0, right? The degree is 1. And here you have x0, y1. The degree is 1 when you add the 2. And here you have x0, y0. The degree is 0. So with at least one of a, b, and c being non-zero, right? In that case now, so you have all this. So this is a quadratic polynomial because the highest total degree is 2. So for cubic polynomial, you have total degrees to be in 2 variables. So example, p of x comma y, 2x cubed minus 3x squared y plus 5y cubed plus 4. So here the degree is 3. Here the degree is also 3. That's 2 plus 1, 3. Here the degree is also 3. Here the degree is 0. Okay. But then the highest is 3. So this is a cubic polynomial. Then quartic and quintic, etc. have total degrees 4, 5, and so on. So for this classification, we always use the total degree. That's what we use. So you have to add the degree on top of x and on top of y to get total degree, to decide the degree of the polynomial. Then you can have classification by number of terms. So we can classify polynomial by the number of non-zero monomials, non-zero strictly. So monomial, that has exactly one term, like maybe you have f of x is f of x comma y to be 7x cubed y squared, f of x comma y to be minus 4xy, f of x comma y to be 5y raised to power 4. All right. So they have just one term. So that's a monomial. For binomial, exactly two terms. So like x squared plus y squared. So x squared, 1, y squared, another term. So, and then another function will be maybe f of x comma y. You have 3x squared minus 3x squared minus y cubed. So 3x squared y is one term, minus y cubed is another term. That's binomial. All right. Then you have trinomial. So I mean, the idea of binomial, that's why we always whatever you have, you always want to look at it in two parts. So we have trinomial, which has exactly three terms. So p of x comma y, you have 3x squared y minus 2xy plus y cubed. More generally, a polynomial with n terms is sometimes called a multinomial, or simply just polynomial. Thus, you can have p of x comma y to be 3x squared y minus 2xy plus y cubed, which is a bivariate. It has two variables. It's a bivariate trinomial, right? Three of total degree 3. So we are combining three things here. So number of variables, x and y, that's bivariate. How many terms? Three terms. That makes it trinomial. What's the total? The highest total degree. This is 3 here. This is 2 here. This is 3. So the highest is 3. So the degree is 3. So this now is a bivariate trinomial of total degree 3. Okay. So we come to the other classification, which is relatively new compared to the other ones we've been considering. Okay, so we have homogeneous versus non-homogeneous polynomials. So talking about homogeneous polynomials, a polynomial p of x comma y is homogeneous of degree d if every monomial has total degree d. That means that all the monomials, each term you take, the total degree is the same. So example, h of x comma y is x squared. The degree is 2. Here, the degree is 2. That's 1 plus 1, 2. Here it's 2 plus 0, 2. 1 plus 1, 2. Here, 0 plus 2, 2. Because x raised by 0 is what we have here. So here now, because for all the terms in the polynomial, the highest degree is always 3. I mean, it's always 2. So each term has total degree 2. That's what we have here. So x squared has degree 2. Xy has degree 2 again, not 1 plus 1. Y squared has degree 2 also. And then you have so you can say h of x comma y is homogeneous of degree 2, basically. So another example, you have k of x comma y to be 3x cubed y raised by 5 minus 5y squared, 5x squared y raised by 3. So 3 plus 2, 5, 2 plus 3, 5. Okay, so x cubed y squared has degree 3 plus 2, that's 5. X squared y cubed. Of course, by the way, don't forget the constants don't affect the degree. The coefficients don't affect the degree. That's why we don't bother about them. So the total degree in each case is 5. So these are homogeneous. So this k of x comma y is a homogeneous, if you like, polynomial or homogeneous binomial of degree 5. Okay. So homogeneous bivariate binomial, if you like. Okay. So then you have non-homogeneous polynomials. So a polynomial is non-homogeneous if its monomials have different total degrees. So example, you have q of x. Most of the polynomials we've been seeing they are non-homogeneous because for each monomial, for each term, the powers are different. So q of x comma y, you have 4x cubed, the degree is 3. X squared y, the degree is 3, that's 2 plus 1, 3. Then 5y squared, the degree is 2. And then minus 7, the degree is 0. So as far as you have one degree that is different, it means that it is a non-homogeneous polynomial. So the monomials have total degrees 3 for this, 3 for this, 2 for this, and 0 for this. So q of x comma y is non-homogeneous. So our earlier polynomial, which is p of x comma y, 3x squared y minus 2xy plus y cubed, has monomials of total degrees. This is 2 plus 1, 3. Then 1 plus 1, 2. Then this is 0 plus 3, 3. So it is also non-homogeneous like that. So that's the idea. And then that takes us to the questions that you want to try your hands on. So first, use this exercise to check your understanding. For each polynomial below, list its monomials and compute. Compute degree in x, degree in y, total degree. Of course, that's pretty easy. For the first one, for instance, the monomials are 5x squared y cubed minus 4xy y raised power 4. Those are the three monomials. Then the degree in x for this is 2. The degree in y is 3. The degree in x here is 1. The degree in y is 1. The degree in x here is 0. The degree in y is 4. Okay, total degree for each one. This is 5, 2, 4, basically. Okay, so try the others. Classify each polynomial as homogeneous or non-homogeneous. If homogeneous, states its degree. Okay, so here, this This is 3, 3, 3, 3. So this is homogeneous of degree 3, all right? Right. Then here we have 4, 4, 4. So this is homogeneous of degree 4. Then here we have 4, 3, 2, 0. So that's 3 plus 1, 4. 1 plus 2, 3. Then 2 plus 0, 2. 0 plus 0, 0. So that's 4, 3, 2, 0. That is non-homogeneous. But of course, the highest degree is 4 for sure. So this is a non-homogeneous polynomial of degree 4. Okay. So we have the third set of questions. For each of the following, determine whether the polynomial is linear, quadratic, or cubic by total degree, and whether it is a monomial, binomial, or trinomial. For L of x, comma y, right? So of course, this is a trinomial because that's 3 terms, definitely. And it is of degree 1 because this is x raised to power 1, y raised to power 1. So 1 plus 0, that's 1. 0 plus 1, that's 1. Then 0 plus 0 is 0. So 1 is the highest here. So you pick that. For Q of x, comma y, degree 2, degree 2, degree 2. Okay, so that is, boy, because it is 2, that's quadratic, and it is a trinomial too. So now this is binomial because that's 2 terms, and the for the degree, so this is 3 and 3. So that is a binomial or a binomial of degree 3, basically. All right, and it is homogeneous, of course, because it is 3, 3. I mean, this is also homogeneous like that. And 7x squared y cubed, this is just a monomial, the total degree is 5. Then give 3 examples of each of these. So a bivariate homogeneous polynomial, bivariate homogeneous polynomial, right? So maybe I can try that. Bivariate, a bivariate homogeneous polynomial. So it has 2 variables, of course. So we have p of x, comma y. So that's bivariate automatically. Homogeneous. So maybe we have 3x squared y, okay, minus 7x y squared. So it's bivariate because it has x and y. It's homogeneous because the degree 3, 3. Okay, so that's a bivariate homogeneous polynomial. So we have bivariate non-homogeneous cubic polynomial. Bivariate. Oh, okay. Well, interestingly, this also fits into it. Oh, is it non-homogeneous, right? Bivariate non-homogeneous cubic polynomial. Okay. Bivariate. Oh, that one. Oh, that one is quadratic, right? I think I got. Oh, a bivariate quadratic. Bivariate quadratic. Okay. So this can maybe just be. This can be x. This 1, 1. Okay. So that's bivariate quadratic. Sorry, that's my mistake right there. So it'll be 3xy, 3xy minus 7xy. That's bivariate quadratic because the degree is 2, degree is 2. Bivariate quadratic homogeneous because it is 2, 2. Then next, we have bivariate non-homogeneous cubic. Bivariate non-homogeneous cubic. Okay, so bivariate non-homogeneous cubic. So again, p of x, comma y. Okay, those 2 terms. So bivariate non-homogeneous cubic. So we can say this is x y squared. Bivariate, it has x and y already. Non-homogeneous, so maybe plus 7xy. Okay, it is cubic. It is bivariate because that's x and y. It is non-homogeneous because the degree here is 3, the degree here is 2. So it's non-homogeneous. It's cubic because the highest degree is 3. Okay. And then the last one, we have polynomial in 3 variables of total degree 2. Polynomial in 3 variables. Okay, that's trinomial. So a polynomial in 3 variables of total degree 2. Okay. Trinomial degree 2 polynomial. Okay, so we have p of x, comma y. So it's trinomial, so it's going to have 3 terms. So maybe we have xy minus x squared y cubed plus, so it's trinomial degree 2. Oh, okay. I think I'm stepping. Okay, let me just make it easy. X squared minus xy plus y squared, okay? Trinomial, so it has 3 terms. Then degree 2, this is 2, 2, 2, okay? Of course, it doesn't have to have 2 to be degree 2. In fact, this could just be y, right? Trinomial, 3 terms, degree 2. This is 2, 2, 1. Okay, but the highest degree is 2. So that's a trinomial degree 2 polynomial. Okay, so with this, we come to the end of this interesting video talking about polynomials in several variables. Thank you so much for listening. Let me know how helpful this is for you. And if there's something you'd like me to try out, feel very free to let me know. Of course, we want to try your hands on the practice questions as much as possible. If you have subscribed already, I thank you very much. If you have not subscribed, of course, you want to go ahead and do that right away. So you can always, and then you hit the notification bell so you can always get alerted each time a new video is released. Having done that, you could also click on join to become a member of this channel, right? You want to click on join to become a member of the channel. And at the highest level, we can have a hangout, like face-to-face or online, to talk about whatever interests you on my channel, right? Ultimately, don't forget to to comment, like, and share either on YouTube or Facebook so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.